I did mention your name in the video. I said, sorry, Will, we forgot to record the first couple minutes. And then I didn't even load it. Okay, 39, common and natural logs. Like I said, we introduced them. We found them on our calculator, but we're going to kind of get a little more in-depth learning into them and where they come from. We use them to solve. Everything has its inverse. So E is an inverse of an ln, and they undo each other when you guys work with them. So instead of saying log base E, we don't write it that way, we write it that way. Would you be wrong if you said log base E? Probably not, but I bet Newton would mark it right if your answer had to be that. So just realize a log base E is an ln. The number E is 2.71 nego, and it's a irrational number, kind of like pi. I think I mentioned this, but I'll just double check in case some kids hear, some kids are not when I say certain things. But it's this common ratio that they found, this constant number that was always there when they were working with continuous growth, early mathematicians. And finally they realized, wow, when continuous growth is that we always calculate and get the same exact number, 2.718, blah, 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 and they get this common ratio that some things are being times by. And so that's kind of where E came from, kind of like how I said pi was the common number that they found when they were working with circumference on circles. And it had to do with radians, like the length of the radius of a circle applies to how many radians you can get around the outside edge. So they realized, wow, there's this common number, 3.14, and there's two of them. Anyway, so that's kind of where some of these used numbers come from. I actually went to a conference, and it says, and we went to this session, you can imagine it wasn't as boring as it sounds, but it actually was super interesting, even though it was boring. But it was like all of the interesting places we find E. And then that was one of my conference sessions. And it was actually pretty dang crazy because I actually never gave the right, I guess I never really realized how prevalent and how cool when you guys work with ratios, how E shows up. It's actually a really cool, cool conference. Okay, we're going to go ahead and write things in equivalent forms. Now we're using ln's and converting them to e's. And so you can still use the around the world type conversion. Like if it's the base of the log, it should be the base of the exponent. So let's go ahead and rewrite a few of these so we realize how to use ln's and e's interchangeably, okay? So what would you guys convert this to? Again, sometimes mentally it helps me to mentally write this as a log base E. Or write it out physically. It's up to you if you actually want to write it out. But it helps me when I do my conversion because I can do that little around the world thing. Whatever the base of my exponent is, right? E to the what? 5 is equal to x. You guys know you've done something right because whatever was stuck inside logs should now be free by itself. So if you have done proper conversions, you guys should notice that situation happening. And backwards, like if something's an exponent and it was stuck up in the exponent, if you convert it properly to a log, it should now be free. So think what's stuck is now free when you just convert them. Cool? And you can write this out. If it says write equation as a, you can write out what that answer is as a decimal, but we're just writing them as their equivalent forms. So how would we do this one? E to the what? Careful. E to the y would be equal to what? 64. So notice how 64 is alone, because it was what was stuck inside the ln, right? So now the 64 is alone. It's pulled out. Cool? So that's equivalent. Let's write another equivalence. What would this one be equivalent to as an exponent?
E to the z.
E to the z. Good. E to the z is equal to 25. Do you guys feel okay then about conversions with ln's and e's? I call it around the world. I convert it going around the world. I start with whatever the base of the log is. Bless you. The base of the log should be the base of my exponent also. All right, this one I want you to go backwards and write them now in its equivalent logarithmic form. So I might choose to go log base e because e was raised to a 0. And that's a 1. But instead of saying log base e, I should have said what? ln. And I would say ln of 1 is 0. Does that make sense to everybody? So when I write it and try the around the world thing, I think going from exponents to logs is a little trickier. So whenever I see an e, I start by writing the log, and then I next put the base. Okay? So since my base is an e, I put my base. What is e raised to that needs to go by itself? A 2, and then the 7.4 goes in the inside the log. Okay? And then try e around the world again. E to the 2 is equal to 7.4. Okay, that makes sense. But I don't write it log base e, so what should I actually write? ln of 7.4 is equal to 2. You still okay about that? One more. I have a log base e. What goes over here by itself? X, because it was stuck up in the exponent, right? And then what goes in the log? 16, but this is actually what? ln of 16 is x. And you guys can always check yourself by going backwards. E to the x is 16. All right, give me a gauge on conversions for you. Being able to convert from log to exponent to log when there's names and ln's. I'm just kind of getting my little gauge. Side down. Those conversions going okay? Would we like another, or do you think you'll get okay in Newton? Will we do okay? If you run into some problems, let me know, okay? If you're struggling on those ones. I think we're going to get to practice them a few more times anyway, and we get to solve on lesson 40. So by the time we're done with lesson 40, I'm hoping you see it a ton. Okay. We want to just bring your awareness to your calculator and where these buttons are. So let's just find a couple. Will you guys type in ln of 1.43, get that decimal, and double check that you get my answers that I'm going to put up here for you. Okay, ln of 1.43, ln of 2, double check that you're finding the right button and using the second, or ln's its own button actually. E is the exponent, so you don't even have to do second. You can literally just click ln. Be really careful, this one's extra tricky. And make sure you don't close parentheses too soon. Make sure whatever is in the log is inside both parentheses. And then you would have had to times by an e to the 7. And let's just make sure you guys are putting that in your calculator correctly. Check that you get 8.6715. Would you guys see that and see if you're doing some calculator work? All right. Okay. We're going to use properties of logs to simplify quickly. And I want you guys to use inverses and some of the stuff we already learned that other day. We learned the quick ones. Like, what did we learn whenever you guys try to ln a 1? It's always a what? A 0. It's always a 0. And we learned it because no matter what a base is, in order to get a 1, it had to be raised to a 0. So this has to be raised to a 0 when you do the around the world stuff. So we've learned using those properties, hey, anytime I log a 1, it's always going to be 0, no matter what the base, even an ln with a log base e. This one we can do really quickly. Who sees it right off the bat what this one is? Really fast. ln undoes an e. So what is it? -7. Okay? So the better you guys get at realizing what are inverses of each other, and they essentially undo each other, and you guys will be able to do these properties pretty quickly. Okay? All right. Awesome. Let's go ahead and start talking about, let's remember what we learned on a different lesson so we can move forward with, we want to be able to graph and work with the inverses of ln's and logs as well, okay? So we're going to go ahead and just like recall a couple things that we've already learned, and then look at these inverses because they're inverses of each other and how they look on the graph together. Okay. So here's a recall for your logs and exponents and how they're inverses of each other. We did this at an earlier lesson. What do we know the inverse of a log, or sorry, what do we know the inverse of a 4 to the x being? A log base what? What's the inverse going to be? A log base. My exponent's a 4. What's my base of my log? A log base 4, right? So let's just recall the graph and what it looks like and how everything about logs and exponents are just inverses of each other. So we're going to find the domain, we're going to find the range, the equation of the different asymptotes, and we're going to create some tables with the way the graphs look. I'm going to go ahead and zoom and make it look small so we can do this together. Let's go ahead and go through the f of x first, and let's state the domain. What's the domain for all exponents? All exponents. Is there anything that we can't plug in to these x's? No. Nothing we cannot plug in, no restrictions. What did we learn the range was though? Because no matter what I plug in the positive and the negative direction, I'm always going to have some sort of number, right? Do I ever touch 0? Do I ever go below 0? So we learned that the range was 0 to infinity because there was a horizontal asymptote at y equals 0. I'm going to say horizontal asymptote at y equals 0. This was clear back during lesson like 33 when we learned the graphs of these, right? I think, or 36 or maybe. We learned that I can, we found intercepts on this one. If I try to plug in a 0 to that, so we can even use this table to find some values. But what's a value at? Well, I'll get to that in 1 second. If I plug in a 0, what do I get? 4 to the 0 is 1. We learned that we always have a y-intercept at 1, and then will I have an x-intercept on these ones? Not when my asymptote's at 0, right? Because there's an asymptote there. So let's just get a couple values, and typically on exponential models, I usually do -1, 0, and 1, because that's about where things take off. If I go much further in this direction, it's kind of a flat line. If I go much further in this direction, it's super, super steep. So that's kind of the best area to get like some basic values. So when I plug in a -1, what's 4 raised to a -1 do to my 4? Flips it to, not negative, but it flips it to a 1 over 4. So 1/4 is about, is 0.25, right? Sorry, I made that look messy. Excuse me. So at -1, we're at a 1/4 about. We already know we're at 0, 1 because we found the y-intercept. So what, when I plug in a 1, where are we at? 4. So 1, 2, 3, 4. So I come along my asymptote, and then I get to take off like that. Okay? Now I'm going to go ahead and worry about the log in red. We're going to do the log 1 in red. What did we learn about everything? Like, what's going to be this one's domain if you were to look at F?
It's going to be 0 to
Swapped. Everything about the x's and y's are swapped. This one's going to be 0 to infinity. So what's this one's range going to be? Or sorry, if you look up at this one's domain, what's this one's range going to be? All reals, right? -infinity to infinity. This one had a horizontal asymptote at y equals 0, so what does this one have? A vertical asymptote. Instead of at y equals 0, it's at x equals 0, right? And then we had a y-intercept at 0, 1, so what do we have on this one? An x-intercept at 1, 0. So let's just go through some of these key characteristics and kind of do that. Now, what else should be true with my points? What can I do with every single one of these points? You can do what with the x's and the y's? Switch them. And I will have a value at 1/4, -1, 1, 0, and 4, 1. So I have one at 1/4, -1, 1, 0, and 4, 1. And so notice what they look like when they're put on a graph together. Do they look like they're inverses? Are they reflective over the line y equals x when we learned about inverses? Back in lesson 33 or whatever the inverse lesson was. Now, can I find the values of this? Do I have to always graph 4 to the x to get my word graph for log base 4? Could have I been strategic and just plug these values in? Yeah. If you guys purposely remember the log properties, logging a 1 will always give me a 0. Logging a 4, because my base is a 4, would have always given me a 1. I could have plugged in a 1/4 myself as well. I could have said, hey, a log base 4 of 1/4, I can manipulate this and figure out what 4 needs, how do I manipulate it to be a base 4, and it would have given me my values too. So you can choose to plug in stuff. You don't always have to graph y equals 4 to the x and switch the x's and y's. Alright, but that's kind of like a quick rundown of what we already learned about inverses, okay? So we kind of learned about how everything with the x's and y's are swapped. So now that you know that, let's do this with E and ln, okay? So the next slide talks about how your e's and your ln's are also inverses of each other. And so we're going to go through and do kind of like the same thing, okay? Your e's domain is going to be all reals like all exponentials, right? What's its range going to be like all exponentials without any other shift? 0 to infinity, just like the other exponentials. We still have an asymptote, a horizontal asymptote. at y equals 0. Oops, we will have a y-intercept if I plug in a 0. E to the 0 still has a value at 1. So far this behaves like every single exponential graph you guys have worked on so far. If I wanted to get a couple more values, I already have my y-intercept, I could plug in a -1 and a 1. Like, if I plug in a -1, e to the -1, it's technically 1 over e, which is some decimal. And then if I plug in an e to the 1, that's just e, which we already learned is 2 point what? Then we learned e is 2.7372, 7 something, 2.72. Does anybody know what 1 over e is? Can someone find that for me? To tell me what this decimal is? Here's mine. 1 over e, and then if it makes you do an exponent, you just do a 1, e to the 1. Go ahead, Cars.
0.367.
Perfect. You said 0.367. Okay, so it's this decimal, a little bit higher than the 1/4. We have a y-intercept, and then e is 2.72. So this looks a lot like all of our exponential models. It's just decimals. That's the only bummer about this, right? All right, so everything with a log or an ln, the f inverse is going to be ln of x. Okay, domain is what, range is what. This is going to be, let's go ahead and do everything on this one. Domain is, let's do this in red actually. What's going to be this one's domain? It's going to be 0 to infinity because the other one's range was 0 to infinity. Its range is going to be all rails, right? This one's going to have a what asymptote? It's going to have a vertical at x equals 0. Yep. And this one had a y-intercept at 0, 1. This one's going to have a x-intercept at 1, 0. Right? Now I can just flip-flop these values. For instance, I'm going to have a value at 0.367, -1, and at 1, 0, and at 2.72, 1. And so we have this graph completely flip-flopped. And it's going to look like an inverse still. So it is reflected over the line y equals x. Okay? So hopefully with all of your guys' practice that you've already gotten, this just kind of solidifies, and now we just added graphs to it. Okay? So we pretty much have that section done. This is the last question. That is kind of close to something you may see. Let's just look at this question. I like us being able to look at graphs. One of the biggest things they want you guys capable of, because to be honest, some of this baseline foundational stuff, for you guys who might be STEM direction and more scientific fields direction, this just gives you guys a baseline. You guys really, really get into the fun stuff when you get into your guys' more applied classes. But a huge part for any STEM direction type careers is being able to look at a graph, interpret data. That is a huge part of these classes that we really need you guys to lead with that skill set, okay? Anyway, look at this graph. Use this graph to predict the value of f of t for these given values. So when t is 1, we want to predict predict those values. So if you guys count this, when we look at this graph, what would you guys say at t equals 1? Let's make a prediction. And what are we counting by? Can you guys tell? It looks like we're counting by 4s because this is like 4, 8, 10, not 10, 4, 8. That looks like I have 10 tick marks, right? So 12, 16, 20, 24, 28. It looks like 32 and 36. So it looks like we're counting by 4s. So, and then this looks like I have 10 tick marks as well. So what's it asking me to find when I say when t is 1? I go where? I go along the x-axis at 1, and I go up and I say, what is it? What's f of t, or f of 1? 16. F of 1 is at 16. What's it asking me when I say at t equals 7? I I go on the x-axis, 1, 2, 3, 4, 5, 6, 7, and I go up and I mark it, and where does it look like it's at?
32.
Very good, f of 7. So even though they didn't say find f of 7, they said it in a roundabout way, right? They said this represents my function, and this is for t equals blank. They didn't say find f of 7, but you guys should interpret that they said that's pretty much me asking you to do f of 7 is 32, okay? So that is lesson 39. Again, we're going to be rearranging some things in the future so that this last little flow works great. Okay? So the only thing we have not really gone over is your guys' solving just exponents. We've worked on them a little bit, but we're going to work on them just kind of as a final using all the skills. Now we've learned logs. Logs was last lesson. We just talked about common logs today. And so now we're going to, or natural logs, and so now we're going to kind of solve. So let me jump to a new recording.